Hello, hello. Okay, so we will do a problems with a distributed load, and we will have two different members of the structure, one that is submitted to normal stress and one that is submitted to normal and shear stress. And the question is, what will be the maximum load, the maximum distributed load W here, knowing that the structure is made of two pipe, like tubing pipe, 4 centimeters by 4 centimeters with a thickness of 0.5 centimeters, and that the maximum stress of the materials is 16 megapascal, and the maximum shearing stress of the material is 18 megapascal. So we kind of know the limits of the materials, how much it can handle. We know the sections, what they'll look like, and we wonder, okay, so what is the maximum load we can apply to it? What do we start with? Always. We start with free body diagrams, and there's two different parts. There's the vertical member and the vertical member BC, and the horizontal, not horizontal, but the one at an angle AB, where we know some informations, where we know the force. And let me re-explain that. We don't know the force, but we still need to start with something that we kind of know. So we will start with the program BC. Okay, you will see what I mean. BC, B, and C. And we have this distributed load that is equal to W. And we know that the distance is 3 meters. So it's a rectangular load. Remember in statics, rectangular will be at the center, and that will be the max load time the distance. So that will be 3W. And we have forces that we don't know at B. We know the direction of the force because AB is a two forces member, because we don't include the weight. So we will have BC, and because 3W is to the right and creates a negative moment about C, this force at B must create a positive moment, so it should be to the left. BC, so that will be FBC, and we know the angle because we are in a little 3, 4, 5 triangle, like this. 3, 4, 5 triangles, very convenient 3, 4, 5 triangles. If you don't remember how to play with the 3, 4, 5 triangles, go in my video in tips for mechanics of material or something like that, in one of the beginning of the modules. I put all the videos about concept that we see again and again and again, like those 3, 4, 5 triangles there. At the pin C, it's a pin connection, so we have two reaction. CY, that will be up. We don't know the value, but they will be up because FBCY will be down. So we have CY, and probably CX will be to the left because the 3W in the center. Oh yes, yes too, because if we do the moment about B, 3W create a positive moment, so CX must create a negative moment. So let's solve for that. What do we do when we have a pin connections to unknown at C for the equation? Remember, let's do the equation of equilibrium, and we will start by sum of the moment about C. About C equals 0. So what do we have? We have 3W, that's create a negative moment, time the distance there, that is 1.5 meter. And we have the FBC, but just the FBC on X, that create a positive moment. So plus FBC time, so we use a 3, 4, 5 triangle, so time 4 divided by 5 to have just the complement on X. So we are looking just at this complement there. And time the total distance, so the total distance from there to there, that is 3, equals 0. So we have FBC equal 3W times 1.5 divided by 4 divided by 5 times 3. Okay, so FBC equal, we can remove the 3 and the 3. The 5 can go on the top, so 5 times 1.5, that will be 7.5 fourths. Or we can also write this 15/8. Oh, and don't forget the W. Okay, and W will be in kilonewton time meter, so FBC will be in kilonewton. Okay, and I put kilonewton because that will be probably some very high load. So we have FBC. Let's keep going with our equation of equilibrium. So we did MC. We can do sum of the forces on x equals 0. So we have minus FBC on x, that will be 4 divided by 5, plus 3W minus Cx equals 0. So FBC, this is minus 15.8 W times 4 divided by 5 plus 3W equals Cx. So we can simplify this. So 15 divided by 5, this is 3, so minus 3W, and 4 divided by 8, this is 2, plus 3W equals Cx. So we got Cx equal 6 half minus 3 half equal 3 half of W. So we find Cx, and let's find now sum of the forces on Y equals 0. Okay, so we have minus, minus FBC on Y. So on Y, that will be the 3/5. And plus CY equals 0. So we got CY equal FBC. FBC, we found 15.8W times 3 divided by 5. So CY equal, so the 15 divided by 5, that's 5. So 5 times 3, 15. 8 times W. Is correct? Oh, not 15. 3 times 3, 9. Sorry, 9. And this is also kilonewton, kilonewton, etc. So now that we have the forces, okay, we found the forces FBC, we found the forces Cx, and we found the forces Cy. Let's look at the stress in each member. Let's start by, okay, that was now the step number 3. Let's put it there. I will look at the internal forces in AB. So I will use free body diagram again, but for AB. Oops, let me do it again. Okay, A, B, and we found FBC equal 15. That was down and left on BC, so that will be up and right on AB. And we know the value. Maybe a little bit bigger so we can see it. That will be 15.8 W on both sides. So if we cut there, we have only normal stresses. And oops, this is also the 15.8 W. So what are equal the stress? The stress, the normal stress, are equal to tau equal the force divided by the area, right? And what we know is the tau max will be equal to the force, so the 15 divided by 8 times W divided by the area. What is the area? We need to find this area. We didn't find it yet. So the area in millimeters, because that will be we will compare that with megapascal. It's a square of 4 times 4, so 40 times 40 millimeter square minus the inside. So we have the little, this one is 40, and because the thickness is 0.5, so 0.5 on both sides, we'll remove 1 centimeters on both sides, so the inside is 30, so minus 30 times 30. So the area of this one is 700 millimeter square. So now let's solve for W. Tau max, sigma max, sorry, sigma max is 16 megapascal, that is provided. So we have, oops, I will go there, 16 megapascal time A equal 15 divided by 8 W. So we have 16 time, we say 700 times 8 divided by 15 equal W. That gives us a max W of 5,973 Newton time meters, or 5.97 kilonewton time meter. This is the max W based on the normal stress in the beam or in the member AB. Now we need to do, so we did the member AB. Now step number 4, we need to do the member BC. So oops, free body diagram. Free body diagram of BC, like this. C-ax, now we know C-ax. Okay, we know FBC on the top, that is down. So this is your FBC, that is 15.8 W. We know the C-ax to the left, that is 3/2 of W. And we know the CY up, that is 9/8 of W. And after that, we have the little distributed load everywhere. Right? So normal force, the max normal force, if we look at there, the max normal force is 9/8 of W. So here, the max normal force is 9/8 of W. And this is less than the 15.8 of W. So the member BC is submitted to a larger normal force and normal stresses. So we don't need to find the maximum W for the bar, the beam BC, because it's lower anyway than AB. Now let's look at the shearing force. Where are the largest shearing force? So here we have the 3/2 of W. This one is 15.8 of W. And if we look at just the shearing force in that direction, that's even lower, because we have a little 3, 4, 5 triangle. So that will be 4/5 of 15.8. That is less than 3/2 of W. So here in the beam BC, the max force, so the shearing force max will be, we will have to compare with the fact, with the 3/2 of W, the max shearing force that is on the bottom, divided by the area. So the toe max for the shearing is different than for the normal stress, 18 megapascal. So we have 18 times the area, that is the same, that was 700, equal 3/2 of W, and we get a maximum W of 8,400 Newton time meter. That is equal to 8.4 kilonewton time meter. So now, what is the maximum load, the maximum distributed load on this beam? We found two different answers. We found, I'll try to have everything on one page. We found a maximum W based on the maximum normal stress, and we found a maximum W based on the shearing stress. And what will be the limit? That will be the lowest, because the lowest W, the beams will be able to handle both of them, but this one will not be able, the first one will not be able to handle the 8.4. So the answer is the max W is 5.97 kilonewton time meter. So if we are not happy with this W, we can change the section, we can change the materials, maybe we can change also the geometry. There's a lot of parameters that we can play with. Hope everything makes sense. Bye-bye.